Welcome. As we start organic chemistry 2. Pick up where we left off. We were talking about acid. No, we were talking about halogenation of these enols and enolates. So we had finished up talking about like acid-catalyzed halogenation. So let's look at alpha bromination of acids. So this is called the Hell-Wohlhard-Zielinski reaction, which adds bromine alpha to a carboxylic acid. So, but it has to be alpha hydrogen. So we're essentially saying to this, so it's going to add this. There's one of two ways to add this bromine. We could either add it with a standard diatomic, or, well, actually, no, I might need both. Sure, let's just listen. Do it as I have written here. BR2, PBR3. That essentially first adds two equivalents to bromines. So adds bromine here. Also makes it acyl bromide, and then in the presence of water, reforms our carboxylic acid. And that carboxylic acid is just like, oh, we know how to do that. That's from last chapter. So, and HBr. Now, the first step is to make an acyl bromide with PBr3, which can then attack bromine. The acyl bromide will be used to find, can be used to find any acid derivatives. So yes, you do need PBr3 and bromine. So the first step is essentially we're saying, oh, we're having we're going from this to our CH2 R, which is then capable of attacking then capable of forming our enol version, which so before we go to there. So okay. Now one of the big reactions we got here is Aldol condensation. That's a pretty big one. That's one we actually do in lab, where we're going to take a ketone and attack on second ketone, and we're going to follow that by a loss of water to form an enone, an alkene ketone. So but we're going to go from the aldol version, the aldehyde / carbonyl alcohol. So we're going to react an enolate. So we're going to react an enolate with another carbonyl to form the aldol, followed by condensation. So the generalized reaction is as follows. So this could be between the same molecule, or it could be between a different molecule. So this is going to be between the same molecule. Could be acid, could be base, doesn't really matter. H minus. So I'm going to skip the enolate forming step, but so we're going to have, okay, ene, this is attacked, C-O-H, R, and then in the presence of heat and acid or base, we're going to then, we're essentially going to dehydrate, so we're going to form water, and then we're going to have our base structure, which stays the same. Actually, sorry. Let's lose that H. CH2 of constant. There we go. So essentially here, forming then, here's the own part, here's ene, enone. So this is our aldol. And then here we're undergoing a condensation. Condensation, we're extracting water. Let's make this an aldol condensation. So real quick, well, not really real quick, but quick-ish. Let's look at the two different mechanisms. How does base catalyzed aldol work versus acid catalyzed aldol? They both work in a similar way, but it just depends on whether you form the enolate first or you deactivate the ketone first. So start with our base catalyzed mechanism. So the base, first thing you do when you're attacking that proton, and we're giving those electrons to the carbon. All electrons have to be conserved. Which can then resonate between our enolate. I know I'm leaving out some lone pairs on that oxygen, but that's fine. Water's my water. Now, from there, that's going to go down to another. Also attack a carbon of the next guy. Thus, forming, as this swings up, form our pre-aldol situation. So step one, step two, reversibly form now in the presence of a acid, or essentially more weak acids, ROH, H2O, anything like that. Got to reform the base because this base catalyzed with negative charge now, deprotonating that. That forms our aldol. Now, this is reversible. This is reversible in all these steps. All these steps are reversible, and so it gives you really, really low yields because of the equilibrium lying heavily to the left. But the formation of the final product is going to be what pushes this guy to giving you pushing this guy to giving you the product you want. Once we get the dehydration, it's going to be too hard to go back. So let's look at the acid catalyzed formation of the aldol rather than the base catalyzed form. So how will this change? Still same thing. You have hydronium. We have a lone pair on the oxygen attacking there, forming our plus designating between that and of course making this proton particularly acidic. Water, attack that, and swing up here. And we have our intermediate, our enol. Now this enol can now attack the next equivalent. This alkene, as this swings down, pushes the lone pair into a negative charge on the enolate, attack here, and form this reversibly as well. And this guy also resonates. We have O plus so in the presence of enough acid, this is already protonated. I almost missed that. Presence of enough acid is already protonated and thus deactivated, and thus allowing this to attack in the first place. The alkene's not typically going to attack that carbon, that carbonyl carbon. But if you deactivate it, yeah, it will attack. That's going to resonate between that form and, of course, that form. Or essentially it's resonating the same way we did here. And then finally, well, to form our product, form our final product, then we have to have some sort of acid, whether this is water to reform our hydronium or an alcohol, doesn't matter, but we're going to essentially extract this off to form form our aldol. So forming our aldol, and of course our pronated acid. So in both cases, we reform our catalyst at the end of the first step. Yields are going to be low because this is all reversible, but this dehydration. So we're going to heat this in an acid or a base, going to give us our alpha beta unsaturated aldehyde or ketone. This is the cheapest, easiest way to form new carbon-carbon double bonds. So we're going to look at first acid catalyzed, then base catalyzed. So for this to work, though, we have to assume that one of these, the alpha carbon, has a hydrogen attached. I'll just put this as R because I don't really care about that. So step one, reversible. Acid pronates this. And from there, water, making this acidic, put it there, swings down, allowing that to be kicked off. Forming our alpha, beta unsaturated alpha. So reforms our acid. So in this case, once again, we pronate the alcohol group and then basically depronate the, which deactivates us to, so making this hydrogen, this alpha hydrogen, more acidic, more willing to be depronated. And so a weak base like water can depronate it. Do it in base, same thing. Same thing, except we attack a different spot first. Same thing. We have H, we have R, H. Reversibly, depronate this guy. Goes to that carbon. So we have minus H. Then we have, well, that swings down, double bond, and that kicks that off as leaving group to reform our base. Same thing. So reforming the acid or reforming the base. But this dehydration can force this aldol equilibrium to the right. When a little heat is going to combine these guys together. But so this base catalyzed thing depends on the acidity of our alpha hydrogen. So the alpha hydrogen, if there is a more acidic position, base catalyzed may not be the best way. But anyway, this is a way to force this to products that we maybe weren't going to have based on equilibrium. So there's many different versions of this. There's like crossed Aldol condensation. So it's when one enolate adds to another carbonyl of a different aldehyde or ketone. It's called a crossed Aldol. So rather than just adding one to the same, so we're doubling up and just chaining them together, instead we're crossing between two. Now this is a little bit harder because it depends on the conditions of the mixtures. You could have 4 different products. Let's just say you could have R1 attacking R2. Say this is the one we want. But if you're not careful, you could have R1 attacking R1. Shoot. You could have R2 attacking R2. Shoot, also not. You could have R2 attacking R1. Also not good. Not exactly what you want. Maybe you're going to get close. But so you want to make sure it's reacting only one way, so you don't have a mixture of products you have to clean up. So, however, if we can put a carbonyl with no alpha hydrogens and is in excess, we can force the product to be controlled for. So let's look at this guy. This guy. This would be like what? 2,2-dimethyl-propanol. This guy is an aldehyde. It has no alpha hydrogens. So while this could be attacked by a enolate, it cannot form an enolate. If I react this with acetal, or essentially ethanol, which has a bunch which has our 3 alpha hydrogens. This is in excess. That's in excess. We can essentially say this will form its enolate, but this won't attack itself because it's going to attack the most readily available compound. And since that won't form the enolate, we don't have to worry about R2 attacking R1, or R2 attacking R2. We only have to worry about R1 attacking R1 and R1 attacking R2. So if I do that, OH minus, we are going to form only this aldol. Which will only condensate to form this enol, or enal in this case. So just looking at that. So we add the aldehyde ketone with the alpha hydrogen slowly to a very basic solution already containing the excess reagent. So we have this basic solution all set up. So we slowly add the reagent, our enolate forming one. Now we can also use, remember our lithium diisopropylamine to selectively make one type of enolate. Remember our lithium diisopropylamine, a very strong base that works very, but it's a weak nucleophile. And it won't react with electrophile, so So remember, as we talked about that, and then so this won't react with aldehydes. And or if it does react with aldehydes, it has side reactions with aldehydes. So lithium diisopropylamine, we can make just one type of inlay stably, add the desired compound as an electrophile. All right, let's look at the reaction we did in lab. We did this Aldol condensation in lab. We had, let's see, so Aldol condensation we did in lab. We used some sort of phenyl aldehyde. Didn't really matter what phenylaldehyde we had. It was a phenylaldehyde, and we used acetophenone. So I was looking at acetophenone. Basically, those phenones will act as a stopgap against alpha hydrogens. The only alpha hydrogen that is acidic is here. The phenol is not going to have alpha hydrogens. It's going to have beta hydrogens, but even so, probably not going to lose those guys. That's going to screw around with our phenyl group. So these guys have, so we only have one type of alpha hydrogen. As we did this, we took our aldehyde, and usually like what, like 0.15 grams or something like that. And we put that in there. We put our acetophenone in there, mix them together, and then added sodium hydroxide. 0.36 mils of acetophenone. I guess it depends on the density of that. Density. No, density of acetophenone is known as 1.03 grams. So in this case, we did use that in excess. But essentially, so what did we do? So we formed, first step would be forming the enolate. That and that. And then we allowed this to attack here in basic conditions. Form that to form our aldol. And then we added that and let that react. Continue stirring, blah, blah, blah. Try to allow that to crystallize. And this one didn't actually need much heat. There, it's in such concentrated base, it's going to go ahead and deprotonate that to form our. One of the advantages of this structure is that all those phenyl groups have a large degree of conjugation. So connecting those conjugations together, the benzene rings to this greatly increases stability. So having this completely conjugated from this side to this side is a very stable byproduct. And so it doesn't take much work to do that. So, but that's just looking at what we did in lab. But this is the reaction we did when we performed this. Now, another type of reaction we can do with aldol is an aldol cyclization. So it's good for intermolecular aldol reactions between two diketones. It's good at making 5- and 6-membered rings. So don't try to make anything really smaller than that. But so let's look at that. R 2 1 2 3 4 5. If we make a 5-membered ring, if I react this OH minus, undergo the intermediate where we form the aldol. There, just to distinguish this OH, and then continued with base. Assuming there's 2 hydrogens there. With more base, keep going, form our or if this is a 6-membered, so one, two, three, four, five, 6. Essentially the same thing. Undergoing a 6-membered prime R. Sorry, the R prime. So, and even so, the carbonyl can end up outside of the ring too. If, like, for example, how would that happen? Essentially, what if instead of, since we're trying to make 5- and 6-membered rings, what if it's, there's our pages. 1, 2, 3, 4, 5. Let's say that 6. 1, 2, 3, 4, 5. 6. No, that's too much. Say we're going to attack there, make that negative, attack there. So as we form that, we're going to have our OH. And of course, next step, aldol. So that's the case where maybe there's no alpha hydrogens to the right of the carbonyl, or maybe just that if the carbonyl is more than the alpha hydrogens are more than 6 carbons away, the other ketone. So we can have a variety of mechanisms. We're planning the mechanism. So we have to know the limitations here. Aldol is a very powerful tool that we can use, but you have to know how to use it. If you see a beta hydroxycarbonyl or conjugated alkene carbonyl, consider this if it could be formed via aldol. So basically saying, if you're saying, how is, you have some sort of compound that is you have this, or if you have this, and it's a synthesize this compound, consider aldol as an option of snapping two things together. Consider the aldol condensation as an option. If you have one of those two functional groups in your ending product, consider, could this have been formed by an aldol condensation? Would that have been possible? So then maybe that's the easiest way to do that. Okay. Claisen ester condensation. That's the next thing we'll talk about. It's a type of aldol that forms an ester enolate rather than a carbonyl enolate. Only problem is esters will have a less acidic alpha hydrogen than the ketone, but they still can be deprotonated with a strong enough base. The enolate esters will act as a very strong nucleophile, similar to a Grignard, though, once formed. And the alkoxy group on the electrophile acts as the leaving group to reform a carbonyl group. So let's look at this. So let's look at our claisen. R O C. I'm going to just say CH3 just to make this easier on myself. We use a strong base. We'll just say OR prime, some sort of alcohol. And it's going to attack it's going to form our ester enolate. ROCO CH2 minus, which is going to resonate with ROC CH2. Now, from there, we're going to this is not going to be a crossed one in this example. This is going to be to the next molecule. Negative attacks there. We swing up to form cross. O minus R. Now here's the thing. Now rather than be protonated, this can, like in the Grignard, swing back down and kick this guy off, which is why a lot of the Grignards can add twice to the ester position. So we reform our carbonyl. So this forms a keto ester. Of course, OR minus. Now, these beta keto esters are far more acidic than ketones. Far more acidic than ketones. So we can keep reacting. And so this region right here is very acidic because it's between two ketones, which are electron withdrawing, if you remember. So I wish I could just erase all these guys. Just so in the presence of base, which we just formed some base, this can keep reacting. So essentially forming this minus, then can have three different resonance structures. Oh, we have that one. We have enolate over there. Like ester enolate. And we also have keto ester enolate. Resonate between those three positions. So we kind of have a problem here. The final step needs to be, before we finish, is to pronate this. The depronation is going to be part of the driving force that is going to keep this here. So the last step is then to add acid again. Look at that, it's either acid adds here to keep this from being removed, or acid gets added there to put it back. So for this in mind, while this needs base to work, strong base, it is only base promoted, not base catalyzed. So this pronation is going to keep it and stop it at this and stop it from going backwards. Stop from going backwards. So that is just one way to make this very unusual compound. There's the Dieckmann condensation, which is essentially a claisen condensation, which takes 1,6 diesters to 5-membered rings, and 1,7 diesters to 6-membered rings. So I gotta draw these guys. I'm only going to do the 1,5 because 1, 2, 3, 4, 5, 6. In the presence of a base, strong enough base. So ethoxy, O minus. Essentially, we're going to have this guy be pronated. That guy's going to attack right there. And so we're going to form byproduct of a cyclic bicyclo, cyclic cyclo ester, keto ester. Once again, just like the crossed aldol, we can do a crossed claisen. So we're done with. But once again, how do we do that? We have to use esters without an alpha hydrogen as our secondary thing. Examples include phenyl ester, formal ester, Carbonates, which we didn't really talk too much about reactions about, but those are like, they kind of have diesters. And oxalates, which is a diester. So those guys are examples of alpha hydrogenless esters that can be added to a basic solution. And then we can slowly add in our ester where we're going to use the enol. A nucleophilic ester can be slowly added, give our mixed product. So, for example, if I use this guy and this guy, which is just a ethyl acetate, use those guys plus that, in presence of our base, strong base. So, so it'll be stepwise. So these are stepwise reactions. So we're going to have our sodium ethoxide, and step 2, we're going to add our protons. Like, oh, I can cross this together to have our diester. We can also cross a ketone with an ester. This works best if the ester has no alpha hydrogens. But this can still occur even if the ester has alpha hydrogens, because remember, it takes a strong base to depronate ester. We can do it with a weaker base for a ketone. Ketones are more acidic. Ketones and carbonyls are more acidic. I can do this with, check that. I do it like just standard hydroxide, and then still have to do the same hydronium. Because we have the leaving group, we're going to have, okay. So, and of course, ROH. So it's possible to do this with a ketone and ester. And it's possible to do this with ester and ester. It's just the same general reaction. You just got to remember that the ester takes a stronger base to depronate it, but once it does, it's a stronger nucleophile. It can act downright like a Grignard. I think we'll keep going. Synthesis of beta dicarbonyls. This is separate from Aldol condensation and claisen condensation. And so what's happening here, the base is going to be acting as a stronger nucleophile than the enolate itself. Now, the base is too strong. So we can't do an aldol, we can't do a claisen. But if we form a dicarbonyl, these are going to be stronger nucleophiles than even this base. So let's look at this. In the presence of this guy, and let's say this strong base, RO minus. If I put this and then I mix this in the halide, this is going to undergo SN2. And then you're going to be like, oh, damn, that's not what I wanted to do at all. I wanted to add a halide onto there. So this is going to remain unreacted. So, shit, did not get the reaction I wanted. But if I do the same reaction with that diketone, remember, or ketoester, this guy, this position right here, guy that's alpha to both ketones or both carbonyls, is much, much more acidic, more willing to take that nucleophile than that RX prime. So if I do that same thing, I can then add that between the two. This is what some of the things you can do. Oh, sorry, R. This is some of the things you can do if you didn't protonate that claisen condensation. We didn't protonate that claisen condensation. We can put in an R group there. That's a very nucleophilic spot. H and X minus. This is far more acidic than the basic alkoxide. So just a quick comparison. This guy, the pKa, remember, of these alpha hydrogens, 20. The pKa of esters alpha hydrogens, we said takes a stronger acid or a stronger base, 24. But the pKa of a diketone is 9. The pKa of a diester, a ketoester, is 11. And if you somehow get this, a diester, 13. So alpha position, these are much stronger. By comparison, remember, water is 15.7. Methanol is 15.5. Ethanol is 15.9. Call. Okay. So let's see. You want to look at this. I'm going to go a little bit long, but I want to give you a couple examples of these dicarbonyl condensations. So just to, oh shit. Okay, how are we doing? Okay, we're still there. Okay. Okay. So just some examples of this in action. We're going to look at how to form malonic ester. Diester compounds or diethyl malonate, we substitute with RX and add an acid to decarboxylate. And then we can add multiple R groups to the alkyl halides and other good leading groups. So let's just look at this. Of how you find. So malonic ester synthesis. So we start with a diester. So a symmetrical diester. So step one, we depronate with our base. Doesn't take much. ethyl. And then we add in our group. So the first step, we depronate, and then the second step, let's see. We have our group in there. O. And then in the presence of acid and heat, we cause this to decompose, and then it forms a substituted carboxylic acid. So it breaks apart to this, and then we lose CO2, and we lose ethanol, alcohol. Two equivalents of ethyl alcohol. Oh, sorry, my bad. Two equivalents of ethyl alcohol. In acid, we are going to substitute the ester down to an acid. Remember that we can force it one way or the other. That in the presence of excess alcohol, we can force an acid to an ester. Presence of excess acid, we can form an ester to an alcohol. So we're kicking off the alcohols. I mean, the either parts of the esters, and you're decomposing this guy, the CO2, one of the esters down to CO2. So this is a convenient way to form a longer chain of add a functional group onto malonic ester. Now, from this position, say we didn't want to decompose that yet. Say we didn't want to decompose that yet. I can further react. Add another functional group on. Do it again. One, our base. Two, another functional group, Rx. And what's it going to be? It's going to have our prime. And once again, do the heat, do the acid, decompose it. Except now our alcohol, our acid is disubstituted. Same byproducts. So how is that actually occurring? How is that decarboxylation occurring? So let's look at this. So from the perspective of this, we have carbonyl. Fixing. So the first thing that happens is my diester forms a dicarboxylic. So what's happening is this, I can here, swinging there. So we have an intermolecular rearrangement to form CO2 and our enediol, which will then tautomerize to our tautomerize back to our carboxylic acid. Now, this is an interesting one. This is an interesting one of just looking at this in general. Of using this diester. I want you to look at this. So this has 3 steps. The product it makes is so bizarre that it's worthwhile. So step 1 is we're just going to say RO minus, our base. Step 2 is this di-substituted bromopropane, 1,3-bromopropane. 3 is I add another equivalent of our base. So essentially the first one is you add that bromopropane to the center alpha position. But that just means you have a long chain bromopropane hanging off that center position because we only deprotonate it once. But by adding a second equivalent of base without adding any more bromopropane means it's going to have an intramolecular rearrangement to form this structure. Which, under the presence of acid and heat, then just forms our cyclobutyl carboxylic acid. So that's just a weird structure, just the idea that it has 2 bromines and 2 halogens, so it can add twice to the same compound without having to add a second equivalent. So one more reaction, acetoacetic ester synthesis. This is a similar, but the final product ends up being a substituted ketone instead of a carboxylic acid because we're taking keto ester instead of a diester. So if I use step 1, our base, step 2, our halogen, halogenated thing. So what it does do, it adds to the alpha position. Presence of heat. Sorry. A little ahead of myself. Heat and acid. Once again, we form a substituted ketone, CO2, and ethanol. So it's very similar to the malonic ester, except essentially at the end, you're cleaving off just that. And you got to remember what acids do. Okay. That is where we will stop for now. The next reaction we will cover on Monday is the Michael reaction, which is what the last major lab. The Michael reaction and Robinson annulation. we'll be able to cover, and that's the last bit of material for this chapter. We are almost done. We will finish all the material on Monday. Predict our last quiz on Monday. Now, hopefully you learned something about organic chemistry. Hopefully my drawing is not so hideous that you can't possibly see. Now, if you like what I'm doing, please like, please subscribe, yada, yada, yada. Have a good day.